So we've looked at our angular quantities, and now we want to talk about how we can do kinematics with the angular quantities. So just like we do kinematics problems with constant linear acceleration, we have similar equations to use for constant angular acceleration. So you're very familiar with our set of equations for constant acceleration, our equation for v, we have equations for x, we have equations without time in them. So our full set of equations that we can use. In rotational kinematics, we have a similar set of equations. Any equation that had a v in it, the v gets replaced with omega. A v naught gets replaced with omega naught. And a gets replaced with alpha. The one that stays the same is t. So here we have our equations for constant angular acceleration, and these do only work when acceleration is constant. In the notation used in the book, they use a theta here. I usually use a delta theta because they've actually assumed that the initial angle is 0 in writing all of these equations. So just to help me keep that in mind, a lot of times I'll use a delta theta. So again, another reminder, for every rotational quantity, there's a linear quantity, and they correspond. So for displacement, we have x for the linear case and theta for the rotational case. Initial velocity would be v naught. For the rotational case, it would be omega naught. Final velocity would be v. For the rotational case, it'd be omega. The acceleration for the linear quantity would be a, and that would be tangential acceleration here. And the rotational motion, it would be alpha. And then, of course, time is the same for both. So here we have another graphic for you that just shows the sets of the equations and how they compare. So we can see they are of the same form, just using the different quantities. Since they are of the same form, and since these problems are very similar, we're going to use the same problem-solving strategy for rotational kinematics as we did for linear kinematics. We're going to be using our grids to set up our givens. So we'll have our delta theta, our omega naught, our omega, alpha, and t, and we'll be able to fill in each of the items here. This is much more similar to one-dimensional kinematics that we did as opposed to two-dimensional, because the vector component nature here is being taken into account by using either a positive or a negative for the two options of rotation, clockwise or counterclockwise. So really, our problem-solving strategy is going to be just like what we did with one-dimensional kinematics. It's just now we're dealing with the angular quantities instead of the linear quantities. So in the next video, you can take a look at an example of applying this to a problem.